Welcome back, folks, to MJ School of Mining and Geology. In today's session, we are going to be dealing with the origin of colors in minerals. Okay, and so basically, we want to understand if the color of the mineral is caused only by the chemical composition, or we will be asking ourselves if only the chemical composition causes color. But you'll soon find out that not only the chemical composition cause color. Sometimes we've got some defects. Sometimes we've got the effect of the what do you call it, the crystal field splitting, and all these things plus the composition are what causes the color. Please stay tuned. Don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. So today we want to understand the main causes of the color in the minerals, and then after that we'll like to differentiate between the idiochromatic, allochromatic, and pseudochromatic colors, and now relate how the color relate to crystal field theory and transition metal ions. And then at the later stage we're gonna deal with the color centers. Okay. So the first questions that we must ask ourselves is, why are the minerals colored? Is it only because of chemistry? No, not only because of chemistry, but the combination of chemistry, the structure, and the physical properties. Okay, that's why the minerals are colorful. But you're gonna find out more when we'll be dealing with the crystal field theory, when we'll be dealing with the idiochromatic, allochromatic, pseudochromatic, and later on dealing with the color centers. And you'll get to understand that the chemistry does not only play the major role in determining the color of the mineral. Okay, so we start with the idiochromatic minerals. This is the color due to the major elements within the mineral's composition. All right, for example, the malachite with it, the copper and the copper ore, it's this green color. This green color is due to the presence of the copper, and then this yellowish to greenish color within the olivine is because of the presence of the iron content. So these major elements are what causes this color. And then once the color is caused by the essential element, then we say that mineral is idiochromatic. That is the origin of the color. That is the idiochromatic. And then on the other hand, the allochromatic is due to the trace elements, is due to minor elements, okay, within that particular mineral, which they get to substitute which get to substitute into the crystal structure of these minerals. For example, in the amethyst, we know quartz is clear, that appears to be clear, but because of the impurities, because of the trace elements, the quartz, the clear quartz would change color. For example, I will give you an example of the amethyst. If we put the iron impurities inside the quartz, it will turn to be amethyst because of this color. And then in the corundum, if we've got the chromium or ion impurities, and then it would give you this what you call ruby. And then the blue topaz is because of the irradiation and contains electrons in defects, or what you call E centers. But I will explain more what you call color centers. Okay. So can now see that the allochromatic minerals, the color within these minerals is due to the impurities or trace elements, and then pseudochromatic is due to the physical effects. Okay, composition does not play a role, but the physical effects promotes this coloring. Okay, for example, here in the mineral labradorite, we see what you call the diffraction taking place, and then this diffraction will give you us what you call this blue sheen, which is what you call the iridescence. Okay, and then you'll understand and agree with me that this iridescence is the one of the best identifying feature of the labradorite. And then sometimes we have the scattering taking place, and then it will give you what you call the opalescence. And then sometimes in, for example, you'd see the fibrous inclusions. Can you now see these inclusions, these fibrous inclusions? Okay, so these fibrous inclusions, they give you the chatoyescence, okay, or the chatoyency. That's what you see in the tiger's eye. Okay, so all these things, they are pseudochromatic. It means the coloring is due to the physical effects but not the chemical composition, as compared to in the idiochromatic and as compared to in the idiochromatic and allochromatic. Now, this is to summarize the idiochromatic, allochromatic, and pseudochromatic. So, let's see the mineral, the malachite. The color is green. The color is green, and but because of the copper is the essential element in the chemical composition of this malachite, then we say it's the idiochromatic. Okay, then in the amethyst, which gives the purple color, is allochromatic because of we have got the ion impurities plus radiation, which causes the color purple in the amethyst. And then labradorite, you remember, it gives us the blue sheen. Okay, and then is pseudochromatic because of the physical effects. Okay, and then it gives us that iridescence, which is the one of the best identifying feature of the labradorite. And the ruby, it will also be the allochromatic because of the chromium within the corundum. Now it will give us that red ruby. I hope you understand the difference between idiochromatic, allochromatic, and pseudochromatic, and how they play, how the chemical composition play a role in the minerals. And then we also have the interesting part, which is the trace element, the transition elements. So the transition elements are these minerals or elements over here. Sorry, these elements over here. Okay, so all these transition elements, they are found within what you call a D block. So, this is what you call a D block. So now the transition elements, they would have what you call the d orbitals. So the d orbitals, they are usually unfilled. The d orbitals, they are usually unfilled. Okay, so but now these transition elements are known for their diverse chemical properties. They're known for their diverse chemical properties, and now these diverse chemical properties are essentially in various technologies. Okay, they're essentially in various technologies. But one of the most interesting part about the transition metals is the multiple oxidation states of these transition elements. Then these multiple states, oxidation states of the transition elements, they allow these transition elements to participate in a variety of chemical reactions and to also act as the catalyst. Okay, to also act as the catalyst. Now you will now, since you understand what transition elements are, you would this is just the build up to understand how these transition elements promote coloring in minerals. Okay, so I want us to start visualize the chemistry. Okay, so this is just this has got nothing to do mainly to do with geology, but to do with chemistry. Okay, so I want us to understand what is happening. Okay, we say if we've got a metal ion, if we've got the metal ion, it's like here. Okay, if we've got the metal ion, okay, the metal ion, I want you to imagine a metal ion with the d orbitals. Okay, the d orbitals or this metal ion, it has got 5 spaces. It has 5 spaces. Okay, now, 2 of these orbitals, we will call them dy dz and then dx squared y squared. These are the 2 orbitals. And then 3 is dxy, dxz, and dxy. Okay, so 2 of these orbitals, they point directly towards the ligand. Okay, ligand the negative charges. Okay, so in this case, so these 5 rooms, these d orbitals, these are what you call the d orbitals. Okay, okay, these are the rooms available. These are the rooms available of this metal ion. Okay, now 2 of these spaces, they point directly toward the ligand. 2 of these, they point directly toward the ligand, but 3 of them, they point in between the ligands. That one thing I want you to understand. Okay, but now what happens when ligand start to approach this metal ion? So before the approaching, okay, before the approaching, we have what we call a free ion. Okay, we have a free ion. So once we've got the free ion, the 5d orbitals, what do you call, they degenerate. Okay, once the metal ion, it's free, it's standing right there. Okay, without interaction with the ligands, we say the 5d orbitals are degenerate. What do we mean when we say they're degenerate? We mean they have the same energy. Okay, but the problem, or interestingly, once the transition, remember this transition metal ion, when it stands there without interacting with the ligands, okay, from the surrounding atoms or ions, we say the 5d orbitals, or those 5 rooms of this transition metal ion, they degenerate. Okay, but when a transition metal gets to be now surrounded by the ligands, then this is that transition metal ion. But now once it starts to be surrounded by these ligands, we see strange things happening. Okay, we will start to create what we call electric fields. We'll start to create what we call the electric fields. Okay, these electric fields, they are generated by them the surrounding atoms or ions. Okay, which now the surrounding atoms and ions surrounding these transition metal ion, they interact with these 5 rooms of the metal or transition metal ion, or the d orbitals. So once that interaction, once the ions surrounding the metal ion interact with the d orbitals, we start to see the electric field being generated. Okay, now this electric field will cause the d orbitals to split in different energy levels. Okay, we start to split. Now splitting, it will give you higher energy level, and the lower energy level. Okay, now that is the splitting. Okay, Once these orbitals they split into different energy levels, the phenomenon is what we call the crystal field. Okay, the crystal field splitting. Once this splitting happens, then we call that phenomenon the crystal field splitting. Crystal field splitting. Okay, so but in an octahedral coordination environment, usually, okay, we've got what you call the coordination or octahedral coordination environment. Now, you would start to see this energy level divided into two sets. This is what you call the E set, and then this is what you call the T2 set. Okay, the T2 set. Now, um, which is why we're saying the 5d orbitals split into lower energy orbitals, which is the lower energy orbitals is the space, the room 1, room 2, room 3. Okay, and high energy orbitals are 2. This is dz and the x squared, y squared. Okay, now remember, this is just the chemistry. This is just the chemistry. But I want you now to understand what causes color. Okay, I want you to understand what causes color. Okay, remember I told you that two of the orbitals, these ones, okay, what do? They point directly. They point directly towards the ligands. Towards the ligands. Then these three, they point in between the ligands. So I want you to understand what happens when the ligands start to approach this central metal ion or transition metal ion. So the orbitals, we know that negative and negative, they repel each other. So when the negatively charged ligands get closer to this metal ligand in x, y, z directions, okay, in x, y directions, the orbitals which or that faces the ligands directly, okay, such as the dz and the x squared, y squared, they will experience a greater repulsion because of they are facing directly towards the ligands. And these orbitals, they face directly towards, or they point directly towards the ligand. So the orbitals, these two orbitals, they will feel more repulsion because of the negative from the ligand will repel the negative in the metal ligand. Okay. So, but the orbitals in between the ligands would become or will feel less repulsion. It's like they are less crowded. But these ones which are pointing directly towards these d orbitals, which they are directly pointing the ligands, they usually they get to be overcrowded and they feel the more repulsion. So these three, they will feel less repulsion. Okay. Now, this difference in repulsion, okay, between these orbitals, these 5 orbitals, they cause the energy levels of these orbitals to split into Z or into high energy and lower energy. Okay. But now the um the two orbitals which the two orbitals which is which are these ones, okay, they usually go up in energy. They usually go up in energy. Come in. Um, Okay, so sorry about that. So these two orbitals, okay, they go up in energy, and these ones, these three, they go low in or they go down in energy. Okay, so the difference in energy between these two groups, okay, between these two groups is what you call the crystal field splitting energy. Okay, the difference in energy between these ones. Okay, over here, let me remove this part. This difference in energy. Okay. Okay, remember we've got this high energy and orbitals, and we've got this low energy. The difference or the difference between these is what is this. Okay, is what you call the crystal field splitting energy, or this the the energy gap is what you call the energy gap. And this energy gap, the energy gap will always determine how much of energy do we need to promote electron from low energy state to excitation state, okay, or to move from low energy possible to high energy. Okay, so then the color, okay, the color will be caused by the light now shining onto a mineral. So for example, over here I showed you that when light approaches a mineral, okay, let me scratch these things off. um I I hope you understand. Yes. So we want to understand what causes now the color, why color happens. Okay. So when light hits the mineral, okay, this is the mineral. Light hits this mineral. Okay. An electron from lower energies, d orbital, would, because it absorbed energy, it becomes energized. It will now become energetic, and then it will jump to higher energy d orbital. So it uses a specific color of light or a certain wavelength to do this. We have learned in physics the effect of the wavelength. Okay, we know that the shortest wavelength is the blue, and the longest wavelength is the red end, the blue end and the red end. So this red end, okay, they've got low energy. They've got low energy. The blue end, they've got higher energy. Okay, now um remember I said the energy difference between the energy difference between the higher energy d orbital and low energy d orbital is what you call the energy gap. So the energy gap will play a role, okay, will play a role in determining the color. So these ones, these red end, they've got a low energy gap, and these ones, they've got high energy gap. They've got high energy gap. Okay. So what happens is once the color, there will be a color that will be absorbed, okay, or get to be used up by this mineral. And then when it is used up, we say it is absorbed. But there will be a color which do not or does not get to be used up by this mineral. It will be a leftover color. That leftover color is what we see. It's what our eyes can see. It's the visible light is what our eyes can see. But we see the complementary color, okay, of what has been absorbed. If blue light is what has been absorbed, remember blue light, like I've mentioned, they've got high energy, okay, and they've got high energy, or the high energy gap. So if we absorb the blue light, then we see the opposite of that blue, which is orange. But if we absorb the red light, we see the opposite of that, which is the green color. Okay. So I hope you understand now. that once the light shines on the mineral, there's going to be a jumping. Light will be absorbed. Now that light that was absorbed will promote electron to move from lower energy state to high energy state, and then the other color that was not absorbed is what we see. Okay, now when light shines on a mineral, the energy gap between the split d orbitals determine how much energy is needed to promote an electron. So if we've got a higher or large gap, only high energy or short wavelength, okay, short wavelength, these are the blue, okay, can be absorbed. But if it's small, only the longer wavelength, like red, with lower energy, will be absorbed. So basically, that's what the crystal field splitting theory tell us much about the coloration of a mineral. I hope you understand. If you happen to struggle to understand this concept, you are more than welcome to comment on the comment section, and I will be pleased to assist. But now this it's the a relationship between chemistry and geology. This is the relationship between chemistry and geology. So these d orbitals and the crystal field splitting is the principles in chemistry, but our understanding of this chemistry principle will help us understand the color we see in different minerals. Okay. So I hope now you understand that light when we've got the free ion, these 5 rooms of the these 5 rooms or the d orbitals, we say they are degenerate. It means they've got the same energy. Can you see they are on the same level? They have the same energy. Okay, then we say they are degenerate. Okay, that is when this transition free ion is free, okay, or standing there without interaction with the ligand. But once the ligand start to approach it in from top to bottom, from front to the back, from side to side or left to right, now or in what you call XY directions, now we start to see the splitting. Okay, we start to see the splitting. Then now we gonna see the splitting into high energy orbitals and low energy orbitals. That's what we have seen. So that's why we say the d orbitals are split into high and low energy orbitals as ligand moves towards them. Now but once now we've got this splitting, okay, it's what you call the split the crystal field splitting phenomenon. Okay, now the when light would now shine on a mineral, okay, the lower energy, okay, the electrons in the lower energy, they absorb light, okay, and then because they have absorbed the light, they become energetic. Okay, they would jump to higher orbitals. Okay, they would jump from lower energy to high energy orbitals. Okay, now the color which was not absorbed, okay, not the color, the wavelength which was not absorbed is what will be seen as the perceived color. Okay, so that's why I'm saying this will give us what you call the crystal field theory. This refers to application of quantum mechanics to understand the behavior of transition metals in minerals, specifically the splitting of the orbitals due to their interaction between the central ion, okay, and its neighboring atoms of the ligands. Okay, remember when they were like this, when they were like this here, when they were like this here, okay, we say they are degenerate because they've got the same energy. But once the same energy, because the transition metal ion is free. It's free, does not interact with surrounding or the neighboring atoms. But once the ligands approach the metal ion, then we start to see the repulsions. Okay, now can now see these are the metal or the ligands surrounding these. Okay, now we'll start to see the repulsion, but this repulsion is unequal because some they experience the greatest repulsion, especially those that are facing the d orbitals, these two d orbitals which are facing the ligands. These are facing the ligands, and then this is between the ligands. Okay, this is between the ligands. So this one will feel less repulsion than these ones. It will be greater repulsion. Greater repulsion. Okay, this one will be greater repulsion. Now, and then the energy difference between this high energy level and low energy level is what we call the energy gap. Okay, is what we call the energy gap. So these ligands approaching this metal ion, it will create an electric field, and this electric field will affect the metals and the orbitals. Okay. I hope you understand the effect of crystal field theory and transition metal ion, how they promote coloration in minerals. And the other thing that promote the color in minerals is what you call the color centers. How defects create color in minerals, okay? And so color centers are tiny defects in a crystal atomic structure that trap electrons. So once those trapped electrons they interact with light, they would give the mineral a distinctive color. So the color centers, they are usually caused by irradiation, okay, or they can be caused by heating during metamorphism, or they can be caused by the crystal defects during the formation. So when a mineral forms, it can form with the crystal defects, meaning would have it will have vacancies. So once now an electron filled that vacancy, now that electron will trap light once it interacts with light, then that will give us a light. Okay, and we know also during metamorphism that once we've increased the high temperatures, the you're gonna have what you call the recrystallization. Now that is to say rearrangement of the atoms. Once the atoms they are get to be rearranged, you can cause what you call the vacancy of the or to cause the empty spaces. But now we know nature, in nature, electrons does not love to be floating around. Okay, they would now be trapped within those vacancies. Okay. Now, this is what we say. We know that the atoms are arranged in a repeating pattern within the unit cell and then creating what you call an atom. Okay. But now, the sometimes the ion can be missing, then we create what you call a vacancy. Now, once that vacancy can trap electrons, because we know the electrons, the nature does not allow or like the electron to just be floating around. These electrons would like to feel or be trapped. Okay, within this vacancy. Now, the trapped electrons would absorb the specific light wavelength. This absorption would create a visible light. That's why we say color centers, they also promote what we see. Okay, okay, they also promote coloration. Okay. And so, for example, let me give you example of the quartz, the clear quartz. We know the clear quartz um if because of the effect of what you call the natural radiation, the Si ion can be knocked off, right, from, remember, I showed you example of the arrangement of atoms. So if the Si atom get to be knocked off, and let's say this one get to be knocked off, for example, and then here the electron gets to substitute this place, okay, or get to be trapped. Now, when once light interact with this trapped electron, okay, when the trapped electron absorbed light would now make this quartz to appear gray to black in color, which is what you call a smoky quartz. Okay, but not only that, also in this what you call the mineral fluoride. Okay, sometimes we can have the F ions, the F ions which get to be knocked off or get to be missing, and then electron will be trapped in that side. Okay, and then now once the electron receive a light or absorb light, then we see this bluish purple greenish color. That's what we call the or distinctive feature of the fluoride. And sometimes also in the amethyst, the amethyst is because of the ion impurities plus natural irradiation, as I've mentioned, and then also the blue topaz is the radiation induced trapping. So that's why we're saying the coloration or the color centers, they also promote the colors in minerals. Okay, I hope it make sense. Okay, if you are following, let's summarize everything that we've learned. Okay, the colors, the due to the color origin, it can be either idiochromatic, allochromatic, or pseudochromatic. Okay, and then sometimes it can be due to crystal field theory. Okay, and that is to say transition metals having the the electrons which are unfilled. Okay, and then the crystal would split in energy levels, and then absorption of light promotes electrons between this energy level from low energy level to high energy level, and then now the color which was not or the wavelength which were not absorbed, okay, whatever the leftover, okay, is what we're going to be seeing as a color or as a perceived color. Okay, and we also have got the color centers. The color centers is because of the knocking off some atoms, and then within the creating a vacancy. Then now that vacancy, when it's filled in by an electron, that electron will absorb light, and then that will create visible light. Okay. So I hope you understand, good people. Let's now test ourselves. Let's see what we've learned. What causes crystal field splitting? Okay, that phenomenon. Remember, when the metal ligand is standing there freely, the d orbitals are degenerate, meaning they've got the same energy. Okay, but once the ligand approaches that central metal ion, now there's going to be the splitting, okay, of the energy levels. Okay, now that's why we're saying ligands approaching the metal ion and interacting with the d orbitals. Okay, which orbitals are raised in energy in octahedral complex is the dz and dxy. Okay, what is the energy gap, that is to say, okay, the energy difference between the high and low energy d orbitals. Okay, and we know that the energy gap will determine how much of the energy do we need to promote the electrons from the lowest energy possible to the high energy possible. We've learned about that. And then why is amethyst purple in color? It's due to the ion impurities and the effect of radiation. How do inclusions cause color? They scatter light within the crystal. We've seen this thing, especially in the in minerals. These inclusions, they scatter the mineral, the light. Okay, then that will cause the color. Last but not least, I would like to pause, and then you must guess the answers. Okay. Which of the following is the example of idiochromatic minerals, the color that is caused by the essential elements? All right. Is it ruby? Is it malachite? Is it amethyst? Is it smoky? Okay. What causes the purple color in amethyst? Is it copper ions? Is it radiation ion impurities? Is it chromatic inclusions? Water content? Okay. Which type of color origin is responsible for labradorite iridescence? Is it idiochromatic, allochromatic? Is it pseudochromatic or photochromatic? The color of ruby is mainly due to manganese, chromium, or corundum. Okay? Okay. Cobalt, sorry. What is the color center? A pigment inside the crystal, a center of a crystal twinning, a defect in the lattice that absorbs light, a crystal core. Please, let me give you some time to figure this thing, as this will bringing us to the end of our session. Okay, this is bringing us to the end of our session. Let me give you seconds to figure this thing out. Okay. I hope you got it right, and you must figure what are the answers. And then we know that the malachite is idiochromatic because of the presence of the copper ion as the essential, okay, element. And then the amethyst is because of the radiation and ion impurities. And then the labradorite iridescence is because of the pseudochromatic or physical effects. Okay, the color of ruby is because of the chromium. Okay, and then the color center is the defect in the lattice that absorb light. We know the defect is will create the vacancy, and then that vacancy, when it's filled by electron, that electron will absorb light, and then that what you call the visible light. Folks, it has been a great lesson. I hope you understand. Should you struggle to figure these things out, please comment in the comment section, and I'll be pleased to assist. Okay, this brings us to the end of the session. We are thankful for your attendance, and please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload a new content. And you know what I'm going to say. Until next time, cheers.